Hello, this is MEI Further Maths Core Pure. We're in the Roots of Equations section and on the fifth and final video on solving polynomials with complex roots. You already know that complex roots always come in pairs. Pause the video for a moment while you think about what that means about the roots of a cubic equation. OK, if a cubic equation must have three roots, and complex roots come in pairs, there's an odd root, which must therefore be real. We can see that in the graphs here. If you look at the cubic graphs, you will see that both graphs cross the x-axis at least once. So for quadratic graphs, which must have two roots, although those roots might be repeated, they must either both be real, including the possibility of a repeated root, or both complex. For a cubic graph, we can have all three real roots, or we can have one real root and two complex roots if it only crosses the x-axis once. For a quartic graph, we can have four real roots, or if the graph crosses the x-axis twice, we get two real roots and two complex roots. Or if it doesn't cross the x-axis at all, we get four complex roots. So, complex roots always occur in pairs, and the factor theorem, which you've learned in ordinary maths, also applies to polynomials with complex roots. You now also know about relationships between roots and coefficients for quadratics, cubics and quartics. So that means we have more than one method to tackle problems. Have a look at this one. We're given an equation az squared plus bz plus c equals 0, and we're given one of the roots. We're also told that a is equal to 1, so I'll just cross that out in the equation. The first method uses roots and coefficients. We're given one of the roots, 3 plus 2i, so we know that the other root is 3 minus 2i, the conjugate pair. If we add these two roots together, we get 6, and we know that that equals minus b over a. Given that a is 1, that tells us that b is minus 6. The product of the roots, 3 plus 2i times 3 minus 2i, that's a difference of squares, so that's 9 minus 4i squared, which is 9 plus 4, which is 13. And that's equal to c over a, and as a is 1, that tells us that c is 13. So our equation is z squared minus 6z plus 13 equals 0. The second method uses multiplying out factors. If 3 plus 2i is a root, then z minus 3 plus 2i is a factor. And the other factor will be z minus 3 minus 2i. So our equation is those two brackets multiplied together equaling 0. And we just need to tidy it up. Z minus 3 minus 2i multiplied by z minus 3 plus 2i equals 0. Multiplying out, we get z squared minus 3z plus 2zi minus 3z plus 9 minus 6i minus 2zi plus 6i minus 4i squared equals 0. Because we're dealing with a quadratic with real coefficients, we know that the terms in I are going to cancel out, so that's a useful check that we haven't made any mistakes. Plus 2zi cancels with minus 2zi, minus 6i cancels with plus 6i. And that leaves us with z squared minus 6z minus 4i squared is plus 4 plus 9 is 13, the same equation we had before. So B is equal to minus 6 and C is equal to 13. We can use similar methods to solve problems involving cubic equations. Here, our first method again uses roots and coefficients. We're told that one root is minus 1 minus 3i, so another root must be minus 1 plus 3i. So, the sum of the roots alpha plus beta plus gamma is equal to minus 1 minus 3i plus minus 1 plus 3i plus gamma. That means that minus 2 plus gamma is the sum of the roots, which we can see from the equation, is equal to minus b over a, that's minus 3 over 1, or minus 3. So that means that gamma is equal to minus 1. The other roots are z equals minus 1 plus 3i and z equals minus 1. Our second method involves making a quadratic factor and factorising fully. So our first root is minus 1 minus 3i, so our first factor is z minus minus 1 minus 3i. Pause the video and complete this solution. OK, our second factor will be z minus minus 1 plus 3i equals 0. Hopefully you've multiplied that out successfully to get z squared plus 2z plus 10 equals 0. You then need to find the other factor, and you can do that by dividing your polynomial using the box method. One factor is z squared plus 2z plus 10, and we need to get z cubed plus 3z squared plus 12z plus 10 as our answer. So z cubed has to go in that box, which means that I must be multiplying by z there. That would give me 2z squared here plus 10z. I've got 2z squared, but I want 3z squared, so I need another z squared, and that means I need plus 1 here. That gives me plus 2z there and plus 10, and I can check I've got plus 12z and plus 10. So the other factor is z plus 1. That means the other roots are z equals minus 1 plus 3i and z equals minus 1. Here's another example. Pause the video and try it for yourself first. OK, we're told that one root is 2, so one factor is z minus 2. I'm going to divide my polynomial by z minus 2 to find the quadratic factor. Of course, if you can do this division in your head, that's even better, but using the box method will help you develop the skill of doing these divisions in your head. So, I need z cubed, so I'll use z squared up there. That gives me minus 2z squared. I don't actually want any z squared terms, so I put 2z squared in there, which means I need 2z up there. That gives me minus 4z here, but I only want minus 2z, so I'm going to add 2z. So I need plus 2 there, which gives me minus 4 as my constant term, which is what I wanted. So the quadratic factor is z squared plus 2z plus 2. Now I need to solve the equation z squared plus 2z plus 2 equals 0. I'm going to do that by completing the square. Z plus 1 all squared minus 1 plus 2 equals 0. So z plus 1 squared equals minus 1, which means z plus 1 is plus or minus I, and z is equal to minus 1 plus or minus I. You can use the same sorts of methods with quartic equations. There are plenty of notes and examples in Integral and in your textbook looking at examples with quartic equations. That's the end of this short video and the end of this series on roots of equations.